Hi guys, we continue now solving some problems. This is example 7. Okay, in this example, we would like to make an electric heating coil, okay, electrical heater from 220 volts from the line voltage. And the power of this heater is assumed to be 600 watts. And from this, we will use chrome nickel wire of 0.5 millimeter in diameter. Okay? We assume that the resistivity at 20 degrees Celsius is given by 1.5 times 10 to the minus 5 ohms times meter. So this is the value that you can find from the data sheet of this chrome nickel wire that you buy. It's easy. You can get this from market so easily. And find the length of the wire used, okay, for this one. So what is the length of the wire? In order to get 600 watt, when we apply, when we connect this to 220 volts. Of course, you never connect this directly to 220 volts. What we do is that usually we just wind this to a ceramic like that, and then the total length will be the total length of this thing. So you can never, and this is put to 220 volts, okay, like that. So you just insert. But if you just do this, just insert 220 volts like that, then this wire just glows, okay, and it becomes very hot, and because it will get so hot, then it can easily break, and of course it's that dangerous. Of course it should have a considerable amount of resistance. It's not like short circuit. So otherwise you short circuit to 220 volts and try to draw lots of current, and then the fuse will just blow. But usually what we do is that we just wind this, okay, to a ceramic material, empty or filled. Then we can just just get connected to the line voltage. This is how we do. Okay, so we will find what the length is. Okay, in the second case, if you consider the variation of resistivity with temperature, of course it does. R equals R0, 1 plus alpha delta T. Okay, this was the resistance changing with the temperature difference. Okay, what power will it be delivered? Will be delivered from the coil when it is heated to 1400 degrees Celsius. So now if T is 1400 Celsius, think about this temperature. 1.4 thousand Celsius, it's very hot. You cannot really be near that. So in this case, what power is delivered? Okay, is the question. So first of all, P equals VI. Okay, the power is given by the product of potential times the current. From this we can find current, because 600 is equal to the current times 220. The current will be 2.73 amperes. So if the current is 2.73 amperes, okay, you can find the resistance. Remember that the resistance should be there. This is the resistance of the wire, by the way. Is this wire going to give you a considerable amount of resistance? Yes, because remember that we can treat the wire like this with a radius r, and the resistance is just rho times L over A, the cross-section area, and L being the length of this wire. Okay, maybe we will use this, okay, or not, because the potential is given and the current is given. So from this we can find that this is 80.6 ohms. So we found the resistance of this wire, which is 80.6 ohm, but this is equal to rho L over A. Okay, rho is given and A is given because A equals pi r squared and r is given as 0.5 millimeters. So it's just pi times 0.5 times 10 to the minus 3 squared. Don't forget, you have to convert this 0.5 millimeters into meters by multiplying by 10 to the minus 3. And of course, for the area, you just square it. And from this, as you see, the left-hand side is known. Rho is given as 1.5 times 10 to the minus 5. Then we can find L from this expression. Okay, L from this expression is found to be 10.5 meters. As you see, it's a long wire. And of course, you have to wind this wire to somewhere. Otherwise, if you just leave it alone, it would be a stupid idea. Okay, the heaters are made like that, not like that. Okay, so now we say that if the resistance is given by R0, okay, 1 plus alpha T0 minus T0, this is delta T by the way, T0 being 20 degrees Celsius, okay, and this R0 is the resistance given at that temperature, which was what? Which was just the previously found result, 80.6. Okay, so we start from this and then increase the temperature to 1400 degrees Celsius. And then, okay, we would like to find the resulting resistance, okay? So if the temperature increases to 1400 degrees Celsius, okay, then this alpha, which is given by 0.4 times 10 to the minus 3, okay, 1 over degrees Celsius. Okay, so alpha is also given as a function of Celsius, inverse of Celsius, so that we don't need to convert these temperatures to Kelvin. So if you use all 0.4 times 10 to the minus 3 there and 1420 there and multiply this and add 1 and multiply by 8.6, the new resistance seems to be, okay, 125 ohms. Okay, so the resistance increased because of the temperature increased. If the resistance increases, then the power, which is I square R or IV or V square over R, all these three are the same. Okay, because if you use V equals IR into this part, okay, then you can either get this one or that one. Okay, since the current is given, okay, and R is known, okay, then we can calculate the power, new power, which is now 220 divided by 125, because the new resistance is 125 and the voltage is 220, and we have to square it and multiply by the resistance, which is now 125. Okay, which now the result P nu is equal to 387 watts. 387 watts. Okay, as you see, after this is heated, this resistance is heated to 1400 degrees Celsius, the power that you can get from the system will be smaller, because earlier, remember, at room temperature it was 600 watts. But of course this will not stay, because as soon as you turn on the switch, okay, the temperature of the wire will start to increase. This is how we create the heat, and this, instead of 600 watts, we will end up with 387 watts of power dissipated in this. What is the rest? The rest is going away as Q, heat. Okay, so okay, this is the reason that we use the electrical heater. Okay, so this was an interesting example. Now we go to the example number 8. Okay. Okay, in this example, we have this circuit in this figure. It looks a little bit funny looking, okay? So this is 1.5 ohms resistance connected to plus and minus, obviously, 135 volts, okay? And now we have the point A there, a resistance, and 4 resistances, okay, are connected in series, and this point A, this is point B, okay, this is point B, A, B, okay, and then C is there, D is there, and this is E, okay. So now we have each one of them is connected to the ground, okay, and this is 30 ohms. This one is connected to the ground, which is 100 ohms. We don't write ohms there, we know the units. And this one is connected to the ground like that, and it's 15 ohms. Okay, so don't forget to put these dots there. Okay, so these are all connected. So this is our interestingly looking circuit. Okay, and now let's see what we are given. A 135 volts DC source. This is DC, not AC. Obviously, we're not solving an AC problem. Internal resistance 1.5 ohms. So internal resistance of this power supply is 1.5 ohms. Very small internal resistance. This is connected to the circuit shown in this figure. The long resistor between A and B has a resistance of 60 ohm. So the whole thing is 60 ohm. Okay, 60 ohm total. And it's tapped at 1/4 points. So if this is 60 ohm, we have to divide it by 4 pieces. So each piece, 60 over 4, which is what? 30 over 2, which is 15 ohms. 15, 15, 15, 15. Okay? So now, what is the total energy delivered by the source in 3 minutes? So what is the power delivered from this power supply, of course, in 3 minutes? Okay, this is an interesting question. So now we have to find, okay, as you see, each one of them is 15. This is 15, this is 15, this is 15, 15. All the values of the resistors are given. Now we can start from where? From this one, because this is the first part that we can get, and then from that we get the rest. So this one gives you, now I will put A and B, A there, okay, okay, here, 15 there, 100 there. Now this is 15. Now these two are in parallel to each other. So now what is that? How do you get the equivalent resistance from the parallel connection? It's 15 times 30 divided by the sum, which is 45. Okay, so this is 10. So this gives you 10, right? So this result is just 10. Now this is, okay, connected. So this is 10, and 10 and 15 are connected in series. So 25 connected to 100. So this part, 25 times 100 divided by 125. Okay, so now what do you get? So this gives you 5. 100 divided 5 is 20. So this is 20 ohms. Now the whole thing is 20 ohms, this one, but it is connected to 15. Don't forget this 15 there. So that from this, we can get now, don't forget this point A and B there. This is point A, and we still have 15, and then 15 there, Okay. Now we have 15, and this combination gave us 20. That's it. Okay, this is point B. Now 15 and 20 are in serial connection, so that it's just the sum of the two, 35. So now the whole thing for this one is 35 times 15 divided by the sum, which is 50. Okay, 35 times 15, which is 50. Okay, then how can we get this as simple as possible? So now this is the resistance, and we have to add to 15. So 35 times 15, okay, divided by 50, okay. This is 10, 7, and then this is 3, this is 2, okay, divided by 5. 21 over 2. Is this correct? Let's check. So we divide this by 5, 7 times 5 is 35, and divide this by 10, we get 7 over 10 there, but this is 15 and 10, which gives you 3 over 2, 21 over 2, that's right. And now, this is to be added to 15 to get the equivalent resistance. Of course, we should not forget this 1.5, okay? We shouldn't forget this 1.5, which happens to be the internal resistance, okay? It's given here. So this is R, very small. So there is also 1.5 to be added the result. But now we have to add 15 to 21 over 2. So 15 plus 21 over 2, which is 10.5, okay? Now 25.5, okay? And then if you add 1.5 there, so you get 26 and 27. So the result is just 27 ohms. Okay? 27 ohms. Let's check this again. Okay? Let's see. Let's start from the beginning. 15 times 30 divided by 15 plus 30, which is 45. Okay? So now what do we get? 15, 45, which is 3. 3 divided by 3. 30 divided by 3 is 10. So this is 10, right? 10 is connected to 15, which is 25. Now connected to 100. 25 times 100 divided by the sum, which is 125. Now this is, since how many times 25 in 125? 5 times. So 100 divided 5 gives you 20, exactly. So this is 20. Now if this is 20, it is to be added to 15, which is 35. Now this is 15 ohms, 35 times 15, which is divided by 50, and we just checked this 21 over 2, which was 10.5, and 15 ohms is to be added to this one is 25.5, and another 1.5 gives you just 27 ohms. This is correct. Okay, 27 ohms is correct. In this case, the current then, the current that the power supply delivers in this direction and in this direction, okay, of course, this current, as soon as it comes here, it goes into different branches. But if they are all added, then the same current will flow. So the current then, the total current that this power supply provides will be 135 divided by 27. And then it gives you just 5 amperes. Okay, it gives you 5 amperes. So the current is 5 amperes. Now, the total power is IV, but the total energy is equal to P times T. So you pay this for the electrical bill, you know. So remember that you are given some bills from the electric company for you to pay because of the expenses you made. It's not the power, but power times the time. Because suppose you light a light bulb which is 100 watts, but if you light it in for 10 hours or 1 hour or 24 hours, okay, then the total time should be multiplying the power to get the total energy. This is the money you are paying for, okay? You are paying for the energy that you have spent, okay? So it's just equal to 135 times 5 times 180 seconds, which is 3 minutes, okay? Because it says how much power you spend and how much energy you spend in 3 minutes, okay? Then the energy is 121.5 kilojoules, okay? Because the energy is joules and the power is watts, don't forget, okay? So this is the result. So the energy that you spend is just 121.5 kilojoules, okay? So this may be a complex combination of the circuits in your home, okay? Now, of course, by using this current, we can find this voltage readily. So what is the voltage here? Okay, voltage plus and minus, because this is R equals 15 and the current is what? 5 amperes, then V equals IR. So 5 times 15, this voltage will be 5 times 15, okay, 125, right? Let me check. 15 times 5, 75. So this is 75 volts. So the rest will be here. So the total voltage here, for instance, if this is 75, the total voltage here will be just found by subtracting 75 from 135. Okay, so 135 and 75, 0, okay, 60 volts there. 60 volts. This is 60 volts. Now, if this is 60 volts, you know the current here, right? I1, let's say. If this is 60 volts, can you find this current? Of course. I1 equals 60 over 15, which is what? 4 amperes. So 4 amperes go there. If 4 amperes go there, then this is 1 ampere. 1 ampere. If this is 1 ampere, then the voltage here is just 15 volts. As you see, we go step by step. If this is 15 volts and 75 volts there, 90 volts between A and D, and then the voltage here will be 135 minus 90, or 60 minus 15, which is what? 45. So this will be 45 volts. If this is 45 volts, then what is the current here? I2. I2 will be equal to V over R, which is 45 over 100, which is 0.45 amperes. So this is 0.45. Okay, so if this is 0.45, then this is 0.55. Of course, because the sum of them should give you 1. So if this is 0.55 multiplied by 15, okay, what do you get? 0.70 something, okay? Just they have 7.5, 7.6 something. So, okay, 15 times 0.55, okay? All right, so let's just multiply it by the calculator. It's simpler. Let's do it since we have started. The solution, let's finish it. 15 times 0.55, which is equal to 825. Okay, so this is 825. So this voltage is here, 825. Now, of course, if this is 45 and this is 825, now, what is the voltage here? Okay, the voltage here should be found by just subtracting this number from this 45. Okay, and then from that the voltage can be found. As you see, you go step by step. Okay. All right. So let's solve. Let's go to solve another problem, and we are done with this one. Good. So it was a nice example with some numerics. Okay. Okay. Now we have magnetic field business. Okay. In this example, we have an interesting case. Okay. So say this is X, Y, Z. This X, Y, Z should be this way. Okay. Z should be that way. Now we have a wire which is coming from here like that, going up and rotating like that at some angle and going to the center and continuing from there in Z direction like that. So it's coming. So let's put this like dotted so that we know that it's backward. So as you see, the wire just goes there, rotates and goes back almost to the origin and then continues in Z direction. And the current is given as 5 amperes. Okay. Now this is point A, this is point C. And this happens to be 30 degrees. They say that this is 30 degrees. And the radius is given by R. So this radius is R. This is almost coming here but not touching, right? So there's a little bit error here, but doesn't matter. It doesn't make any difference. Okay. And the magnetic field is inside the page. Okay. Everywhere constant. Be inside page. Okay. Inside the page. Now, a long thin copper wire carrying the current of 5 amperes is given by in the shape as shown like that. Okay. Okay. It is lying in a uniform magnetic field of 3 Tesla. So B equals 3 Tesla. B equals 3 Tesla. And directed along negative Z-axis. So it means inside this, okay? So the magnetic fields are like that. Field lines are like this, okay? So magnetic field lines are like this. Okay. In other words, inside this shape. So it's like circular piece. It's just passing perpendicularly, okay, to this piece, and then, of course, the magnetic field line is along the current, probably causing nothing, okay. The radius of the circular cross section is 0.8 meters. So R equals 0.8 meters, 8 centimeters, 8 centimeters. Find net force acting on the wire. So what is F net on the wire? Okay. Now, the portions of the wire along the axis are not affected by the given magnetic field. Why? Because F equals I L cross B, remember? Now, here, the magnetic field and the current are in the same direction, okay? So that if they are in the same direction, then the cross product gives you 0. No contribution. So the only contribution is from this curved one, this straight and then this part. Okay. Now let's put also O here to specify the origin. Okay, now what is FOA? So what about the force here? The current is going up. So FOA, the force, is I times L R, okay, cross B. As you see, it's 90 degrees. So we don't need to do anything, but now the IRB, right? IRB, which is now we have to find the direction of the force. Don't forget, in this part, the B is this way, the current is that way. So I cross B, okay, I cross B is going to be to the left, okay, to the left. So I cross B is going to be to the left. So now let's write it like that. So I cross B, okay? Because the length is R now, as you see. This L happens to be R there because this left side is R. Since this is semicircle, this is also R, by the way. So now R cross B. As you see, the current is in positive Y direction. So it's the current. Let's write the values first. 5 times the radius, which is 0.8, the magnetic field, times B, which is 3, okay, Tesla. Now the unit, the direction. J is the first vector. B is minus Z, right? Minus K. Remember that IJK, when you go around this loop, it gives you the products, the vector product. I cross J gives you K, J cross K gives you I, and so on. But now what about this? Let's put this minus sign outside and think that this is J cross K. As you see, J cross K is I, and there is a minus sign, minus I. So the result for this vector product is just minus I. Repeat. If there is a minus sign in one of the unit vectors, you just don't consider it. Just keep this in mind. You will multiply the result by a minus sign and do this product. J cross K. How do you do this? J cross K, and you're moving in the correct direction, gives you I, but you use the minus sign and minus I. So FOA is given as, okay, the product of these three, which is minus 12I Newton. Okay, so we found the force which is totally in this direction. So the force is in this direction. Okay, now what about OC? Similar, okay, OC. Now for OC, we have now ILB, okay, ILB, but it's again I times RB, which is 12, but this should be multiplied by sine and cosine, okay? So because now the force will be equal to, okay, this way, okay, the force, and it has two components, x and y components. X components, okay, this FOC, right? And y component is negative, x component is positive. How did I know that this was the case? Because remember that the current is flowing this way and the magnetic field is inside the page like that, okay? And then I cross B goes down. So FOC is downward, okay? Now it has x and y components, and from this, okay, from this, because of the geometry, we can see that this is equal to, okay, just, okay, the result, I will just write the result, but first let's do this, okay? So it's minus 5 times 0.8, okay, 0.87 I plus 0.5 J times minus 3K. Don't forget, this is the magnetic field direction, and these are the values, x and y values of this vector. As you see, x values, if this is 30 degrees, then this is also 30 degrees. Okay, fx is sine, FOC times sine theta, sine 30 degrees, which is this. And then fy is FOC times cosine theta, which is 0.5. Okay? That's right. Okay, in this case, we multiply this by minus 3K, okay, and the result, I cross K gives you, let's see, I cross K gives you minus J, but J cross K gives you I. So that from this, we can write FOC as, okay, 12 times 0.5 I minus 0.87 J. Okay, so this is Newton. Good. Now, FOC is this. Then FAC, okay, FAC, now how can we get this force here? Now let's draw this part again, okay? The current is this way, and the magnetic field is inside. So I cross B gives you this force. The force is always perpendicular to the okay, it's away, right? Like that. The force is like that. The force is like that. So it's like they have pulling effect from three sides. So don't forget, this is A and this is C. This is C. FAC. Actually, it's just the sum of the two vectors of dfx and dfx in I direction plus dfy, okay, in y direction. Don't forget, this is still x and y, okay? So if you can determine this dfx, which happens to be, okay, if this is theta, okay, then of course f of x will be, fx will be given by fac times cosine theta, and similarly fy will be given by sine theta, okay? So now dfx is equal to, okay, dfx will be given, okay, integral, just f of x, by the way, is given by df times cosine theta, okay? And this is IRB, just the product of these three, okay? And now the vector business, but it's now cosine theta d theta. What is the angle now? The angle is, as you see, this is 30 degrees, but the 30 degrees is pi over 6. So the angle is from pi over 6 to pi over 2, because this is 90 degrees now. You have to integrate like that. So now what is that? It's IRB times sine theta from pi over 6 to pi over 2. Okay? But now, sine of pi over 2 is 1, but pi over 6 is 30 degrees. Okay? Sine of 30 degrees is square root of 3 over 2, whatever. You can find this result. So if you do this, then it's just 6 newtons. 6 newton. Okay? The result is 6 newton, f of x. And Fy is equal to simply just sine theta IRB times integral sine theta d theta with the same limits, of course, and it is given by 10.44 newtons. So you get the two forces for this curved part, okay? And in this case, FAC will be given as, in vector notation, of course, 6I plus 1044 J newtons. So this is the result. So we put the results in squares, in rectangles, right? So the net force will be the sum of the three, basically. F net will be the sum of the three. Okay? Just add them up. FOA plus, okay, OA plus FOC, this, plus FCO. FCO. This is ACCO. Okay? Now, if you just add them up, you see it's equal to 0. You get 0, nothing, no net force. Okay? Why is it so? Because this is total closed loop. So if you have closed loop, the force will be always 0. Okay? So net force turned out to be just 0. Very simple. But to get this, we did lots of calculations, as you see. Okay? All right. Now let's see if we have time left. Maybe one more question. Okay, we have 10 minutes left over, so that I will solve one more example and then finish the lecture for today. So what example do we have left over? Right there. Okay. Now, this is now two electrons traveling in the same direction. So in this example, we have two electrons moving in two-dimensional space. So this minus E is the charge of the electron. V1 in the positive x direction is 2 times 10 to the 6 meters per second. Don't forget, if this is electrons or protons or some atomic particles or something, you need vacuum system. You can only repeat this experiment in vacuum. Probably you have this tungsten wire and you heat it up and increase the temperature of this wire so that electron thermionic emission occurs and electrons are just distributed everywhere, and then you probably apply some kind of positive voltage so that some of these electrons just will pass through this hole and go to the right, and this is how you can get this electron. Now, as you see in this problem, there are two electrons, two kinds of electrons which are moving in the same direction. So you can drill two holes so that two electrons are going in this direction and see what they are asking. So now they are separated by a distance of 10 angstrom. Wow, this is really interesting. So the thickness of these holes is like 10 angstrom, which is not easy to establish, by the way. Okay, like 100 nanometers. But using femtosecond lasers, you can do that. And as you see, if these electrons are so near to each other, they will diffract, and there will be some kind of diffraction. Probably on the surface there will be some bright and light, okay, spots. Anyway, you can do this only when you suck the air outside and then repeat this in almost empty space, which is totally impossible. It's impossible to get P equals 0, the pressure inside the vacuum chamber, but you can go as down as like 10 to the minus 9 torr. It's incredible amount of small pressure. Remember that atmospheric pressure is approximately 400 torrs, something like that, 400, 500. Okay? So now think how small the pressure is. Only then, when you suck this air from this vacuum system, then you can do this experiment. Anyway, so they say that this electron is also moving, this one is moving faster though. It's 2 times, V2 is also 2 times 10 to the 6 meters per second. Sorry, they have the same velocity, of course, because they are coming from the same source. V1 and V2 and V1 should be similar. Anyway, so they are moving in the same direction. They give the values of the velocities, and the distance of separation is 10 angstrom, okay, or 100 nanometers. What is the electrostatic force between the electrons? What is that? What is the electrostatic force? What is the magnetic force? let's find electrostatic and magnetic. So what is the electrostatic force? Electrostatic force is K times E squared over R squared. Now K is 9 times 10 to the 9. E, the electronic charge is 1.6 times 10 to the minus 19. But you have to square it, divided by the distance. But this is 10 angstrom, 10 times 10 to the minus 10 meters. Okay? So 100 nanometers, by the way. Okay, so that's it. And you have to square that also. When you do this, you find the electric force as 0.23 times 10 to the minus 9 Newton. Okay? Now, do they attract each other or push each other? Or is it repulsive? Because minus charge pushes electron, minus charge pushes the other electron. It's just repulsive force. So they will probably go away from each other like that if there is only electric force. But now let's see the magnetic force. Let's see the magnetic force. In what direction it is? First, let's calculate. Okay. Now, in order to do this, we know that if this creates a magnetic field on this, this also creates a magnetic field on that. So let's try to find the magnetic field that is produced by one of these electrons. Okay. So magnetic force acting on each electron is going to be the same in magnitude and opposite in direction. Okay. Because remember that F equals QV cross B, and V is this velocity and magnetic field. Now let's see what magnetic field creates this second electron. So if electron is moving this way, okay, so the magnetic field is going inside the page. Okay, so here B1 is inside the page. Okay, because the charge. Okay, if it is inside the page, okay, then V cross B, okay, will be in V cross B is going to be, okay, okay, V cross B will be in K direction. Okay, let's do this. Let's do a perspective study. Okay, so that will be much better. So this is V1 and this is V2, as you see. So by using the right-hand rule, okay, right-hand rule, okay, right-hand rule, if the current is going like the electrons are producing some kind of current, by using the right-hand rule, okay, so it will be creating the magnetic field downward, okay, B1, and now B1 is this way. Don't forget, this is X direction, and X, Y, Z, this is minus Z direction, minus Z, okay, minus K. So now, of course, this is like perpendicular to each other. Now, F cross V, this is V cross V. V cross V will be now in this direction, okay? Will be in this direction. So, what's going to happen is that they will attract each other. So because of this force, you know, okay, so they will attract each other. So instead of repulsive force, the attraction force will be obtained by the magnetic force. Okay, remember that F equals V cross B. V is this way, B is downward, F is this way. So similar for the other cable. So let's get the value of this. So V cross B, we know the direction. So therefore, the magnitude of the magnetic force is going to be just 1.6 times 10 to the minus 19, which is times the velocity, which is 2 times 10 to the 6, and the magnetic field. The magnetic field should be found by how? Okay, how do we find the magnetic field? If the current passes through here, okay, remember that if the current passes through here, then the magnetic field was given by, okay, 2k lambda over r, the distance, okay, 2k lambda over r, okay. From this, you can find the magnetic field and insert here, and then find that really, if you do this, of course, lambda should be defined as the current per unit length. So there are lots of K is known and R is known because it's 10 angstrom. But how can we find lambda? Lambda is, since I equals dq over dt, okay? I equals dq over dt. Now we can do this, okay? Lambda is equal to dq over t divided by L, okay? In this case, the charge is given by L over T gives you velocity. You can find it from there. And then if you put this lambda here, you can calculate B, and then you can put it here, and the total force will be just minus 0.032, okay, K. So it will be in this minus K direction, inside the page, just like here, okay, inside the page. So now, if this is so, then they are opposing to each other. Okay. In this case, the force, magnetic force will be just this much newtons. Don't forget this. If you write this as vector, it's going to be in J direction. Okay. So this is the force on the second one due to this one, or minus J direction, okay, for this one, and plus J direction for the other one. Now, this force, however, for the magnetic field for the second wire will be 0.032 newtons, but this is 32 times, so the result is given by so this is the magnetic field. The magnetic field is given by minus 0.32 Tesla. Okay, when you insert this in this magnetic field, 0.032, you get 0.1 times 10 to the minus 13 J direction. Okay, minus J. So now, as you see, this is electric force, this is the magnetic force. Magnetic force is inside, electric force outside. They are trying to balance each other, but which one beats? Okay, so this is electric force is 10 to the minus 9, but this is 10 to the minus 13, so that the electric force is greater than the magnetic force, so that they will be getting away from each other. So when they pass through these holes, they will probably be getting away from each other due to the difference in the electric and magnetic forces. If they were the same, they would move in parallel, but they are not, okay? The magnetic force is way smaller than that one, okay? How many orders of magnitude? Probably about 4 orders of magnitude, 10,000 times smaller, okay? 10,000 times smaller. So this concludes these solutions of examples, guys. I hope to see you on Wednesday, which happens to be the last lecture. Thank you for listening to me. Okay, so I hope you enjoy. There may be some minor mistakes, some minor language mistakes, and some little problems, but I think that you can bear with me. Okay, have a nice day now.